With lecture for today. Oops, this is January 16th, not January 7th. Um, we're going to review homework one of the calculations in there just for extra safety. And then we're going to talk about distance polygons some more. And at the end of class, hopefully, we'll have a chance to talk about one of my favorite movies, Hidden Figures, which is about the stuff that we're talking about in actuality. And we'll have some homework over the weekend. But before we get to that, let me just remind you that a couple things. First of all, SI, you guys just got out of SI.
Yeah, earlier.
All right, okay. And so the next one is on Monday, and then.
That's last.
Wait a minute, that is last.
Old.
That is, forget about this one. But anyways, the SI schedule, so X this out of your mind. I'll put the right one in. We have, when is the next one? Monday?
But there's no
No, Tuesday.
school Monday. Yeah. So
There's Tuesday.
no Tuesday either. So it's Wednesday at 3 o'clock.
Okay, so you're gonna have to take good notes today. Another thing, make sure to register your iClicker and web courses. Did you get it done? Are you doing it?
Having me reset my password.
Oh, brother.
I know.
Now there was another young lady with the iClicker that came up to the front. Yeah, did you register? Good. All right. And now today's the last day we're going to do practice questions. But on Tuesday, the 21st, that's when we're going to have official class participation begin. All right. So, and almost everybody's registered, but there's still a few of you out there that haven't done it. And remember, you've got to have this for doing classroom work and also on exams. We'll be using it in various ways. And we're not using the Reef app, which lets you use your phone as the clicker. We're just using the regular old school in the room clicker, the iClicker 2, all right, which is pictured up there. Okay. Any questions about clickers and stuff? Yes.
Before the end of the class, so
Yeah, you'll be good. Yeah, just do it right now, real quick, and that'll be good. Okay, let's keep going. I want to do a little recap of homework one. You had this problem up in the Iceland jet up in the North Atlantic. How you're floating around in there, and a swimmer floating along in the North Icelandic jet for 30 minutes. And it gives you a distance. Now here's the distance. There we go. Here's the distance over here, right? Oh, come on back. There we go. All right, there it is. 30. In this instance, 3,086 meters in 30 minutes. So that's your delta X or delta S for some generic direction. It might not be the x-axis. And then 30 minutes, that gives you an amount of minutes and amount of seconds and stuff. And so you want to answer to the nearest meter per second. So here are the specs for this instance of the, now you might have had a slightly different distance. So to get the average speed, you need a delta T. Now delta T is in minutes, so you have to convert, and you want it in seconds. So you multiply by 60 seconds per minute, and so that'll give you 1,800 seconds. All right, and so that's so good. That's the delta T. All right, and then the delta S, the distance, a generic distance is already given, 3,086. And that's, I use the letter S if I'm just giving you some generic spatial axis, not necessarily X, not necessarily Y, not necessarily the Z axis, but the North Icelandic jet axis. And so we'll just call it S. and you just make your ratio, and here it is, 3,086 meters on top and 1,800 seconds in the denominator. And when you calculate that out, it comes out to 1.7144 meters per second. Now, you also have to read the instructions, and they say type in the numeric part of your answer, okay, to the nearest 0.1 meter per second. All right, so that means, so don't, when you're doing these problems, don't type it, try to type in meters per second or anything. It's just the numeric part, okay? So in that case, it's 1.7. So you wouldn't need to type in 1.7144, just round it to the nearest tenth of a meter per second, ding, 1.7. Okay, so there's your answer. And here's what it looks like when you get it right. You can actually look at your attempts once you've submitted them, and WebCourses grades them automatically. And then you can actually look at it. And down here at the bottom, there's the answer that I typed in. And then if you look up at the top, it'll say, yeah, 2 out of 2 points. So you know that that answer is correct mente. All right. Now, a couple things I want to mention to you about these calculation type problems. Now, this was a cinchy one, and we're going to have some basic calculations as we go. And sometimes they'll be in multiple choice format, so you just choose one of the, you calculate, and then you choose A, B, C, D, or E. Sometimes you type in the number. When you type in the number, the position, every time you retake the assignment, you know, so like your first attempt, and then you go to your second attempt, and then your third attempt, and your fourth, you know, usually you have 4 attempts. On each attempt, you might have a different distance or time. So you have to read carefully. And WebCourses does that. You know, that's their design. They change those numbers randomly. You know, I give them a range where I want the distance and a range where I want the elapsed time. And then they give you, you know, some kind of a distance and a time. And it can change randomly on each attempt. So what that means is you can't recycle answers. So if you get this one right, but then you got the question before that wrong, and you want to do another attempt, and you get to this problem on your next attempt, 1.7 might be wrong. Okay, so just read carefully and recalculate. If you got it right once, you can get it right again. All right. And the reason that we have 4 attempts is so that you can use the homework as a study tool. All right. And for that reason, you can usually get a pretty good score. And at the end of the semester, many of you will have like a 90% or higher grade on your homework, which is really, really nice because I think the home is the syllabus. You don't have the syllabus up there. I think the syllabus says we convert our homework into 25 points and our classwork into 25 points. Now, those two together are equal to 1 midterm. And if you're here clicking in class faithfully, you're going to get 25, or maybe if you miss 1 or 2 lectures, you might get 24 or 23, but you're going to get most of them if you're here every day. And if you do your homework and stuff carefully and try to, you know, maximize your pointage on that, you're going to get 24, 25. And so you're going to come in at the end of the semester with a 47 out of 50 on your combined homework and classwork grade, and that's the equal of a midterm. So it's like getting a 47 out of 50 on a midterm, or 48 out of 50 on a midterm, 49 out of 50, 50 out of 50. All right. So just keep that in mind. When you're doing homework. Now, I want to do some clicker questions with you. We're going to continue with clicking, so get your clicker ready. And I want you to do some thinking. We're going to try to work our way through some concepts. Now, one of the things that we used last time was the speed formula. Excuse me. The average speed formula, delta x over delta t. And that works good. We did that. In fact, the Norwegian jet or the North Icelandic jet is an average speed type question where you figure out the average speed. But there's a more generic formula for any kind of average, not necessarily a physics velocity average, but a method of calculating an average, and you probably have done it a million times. So just think, go ahead and write down these 4 distance measurements. You're measuring some, like a dollar bill, half a dollar. You fold your dollar bill in half, 2.8 centimeters, 3.0 centimeters, 2.9, because not everybody folds it the same way. So there might be a little bit of leeway. So you have 4 folded lengthwise dollar bills, and you're all about the same figure, but there's a little bit of plus or minus in there. And so go ahead and write down those 4 numbers. So now you've got, now this is not speeds and stuff, okay? So we're not going to use delta x over delta t. But we can get an average distance here, and that's what we're going to do on the next page. How would you calculate the average? Okay, so this is multiple choice. So turn on your clicker and make sure that it's on frequency BC. And for this, you need your calculator. Start bringing your calculator to class. And if you don't have a calculator, go down to Walmart or even the UCF bookstore and get. Oh, it does? Oh, hold on a second. Oh, that's why I got it, because I got to close this thing. All right. All right, you guys getting it? Okay, I'm getting a flood of answers here. Okay, good. So as I was saying, the calculator that I use is this one. It's a TI-30X. It looks like it's solar too, so it doesn't need batteries. Something like this will be fine. And just start bringing it to class in your notebook. And the reason I want you to get one is because on the test you cannot use your cell phone, not even for using the calculator. And so you have to have one of these babies. Okay, 10 seconds to vote. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys have got here. Yeah. 2.85. And here's the calculation. Just add, and that's basically it. Add them up and divide by how many you have. Okay, so make a note of that. A generic average method is add up how many you have and then divide by the number that you have. So in this case, divide by 4. You have 4 distance measurements, add them up, divide by 4. All right, and hopefully that makes sense to you from way back in 6th grade and stuff, that kind of thing. Now, let's go back to and we're going to actually use this in a few minutes. But I want to go back to the formula for average speed now. So here's our next question, A, B, C, or D. Which of these is actual formula for average speed? Now, V with a bar over the top of it stands for average speed. Okay. So look at each of those formulas. And notice there's no delta x over delta t, so this is a little variation. Okay. 20 seconds starting now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, stop. Let's look at your answers. Ooh, we got some talking to do. There's a little bit of spread in the answers. That's normal. Don't worry about it. Now, which of these is add them up and divide by how many? B is. That's it. All right, so there's an example of add them up and divide by how many. All right, that's a generic averaging method, and it definitely is the case here. All right, now I'm going to mark this one correct. So B is the correct answer on that. Now, let's think about a skate. Anybody here have a skateboard today with you? Okay. In the back, would you like to do a demonstration for the class? Are you brave? Okay, would you take your skateboard? Now, we're going to ask, I'm going to ask a skateboard question here. But first, we need a demonstration. Okay? And what I want you to, now, first of all, what's your name? Joyce. Joyce, I want you to go to the top of the aisle, okay, and mount up on your skateboard. Okay? And then don't roll down, just hold yourself at rest and be ready to start. Okay, so right now, Joyce, she's ready to go down the aisle, but she hasn't started yet, so her velocity is 0. Right? So make a note. At the top of the aisle, V equals 0. Or V subscript I, initial speed is 0. All right? Now, go ahead and give yourself a little bit of a push off and come all the way down here to the front. Go catch her. Go down here and catch her. Okay, Yay. Okay. Now, let me ask you a question. When she got down here towards the front couple rows, was her speed 0? No, she was blazing. All right. All right. So she had like 2.5 meters per second or something. Don't leave yet. I was just gonna say thank you, Joyce, and let's give her a hand. And now you can go back and sit. And so V final, V subscript F, or V2 would be like 2.5 or something like that. Now we didn't measure that, so what we're going to do is just use the symbol V2 for that. All right. Now this question, let's get to this question now. Here we go. All right. If Joyce is at rest at point P1 at the back of the room, then what is the speed there? And hopefully you. So click in your answer. Are you clicking okay? Okay. Okay. Can you show her how to put in BC? Or you could do it. Okay. Good. 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 Now type in a letter. And hey, you guys, when you're doing multiple choice, you just have to click one of the letters A, B, C, D, or E. All right. All right. 5 seconds. 5, 4, 3, 2, 1, 0. Okay. Let's see what you guys have got. Yeah. The average or the initial speed is 0. That's what it means. If I say that something's at rest, you can automatically write down speed equals 0.0 meters per second. Okay, that's what that means. Okay, now let's go and ask another question. Or let's make a note here. Down here, the skateboarder will have a few meters per second of speed. We'll call that V2. So that's like Joyce down here. Now, if we had a speed gun, we could have, timed her speed, which they use that for cars. They don't use it for skateboarders usually. But I mean, they could if they wanted to. And we'd get 2.5 or 3.1 meters per second, something like that. Okay, but let's just call it V2. All right. Now, next question. How does the average speed formula simplify? A, B, or C? So V1 is 0.00 meters per second. V2 is whatever V2 is. And the average speed, add them up and divide by 2, simplifies into one of these three formulas. Would you guys like to dismiss a little early today? Raise your hand if this is your last class of the week. Whoo! Okay, so you guys, I take it you guys, this is your last class of the week, you'd be in favor of dismissing early. See, because it's my last class of the week too. So, but we're gonna walk our way through all this stuff, but we might dismiss a little early today. You never know. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys have got. Nice. 86% of you voted for that one. Yeah, C is the one. Because, V1 plus V2, if V1 is 0, you don't even have to write it in there. So the numerator is just V2. And then the denominator has nothing to do about it, so that's just 2. So your average speed is V2 over 2. In other words, the speed at the bottom, make a note of that. The average speed, and this is assuming a constant acceleration, whatever it is, it's a little bit less than gravity because it's going on a slope. We're not going straight down. She's just getting a little bit of a slope here, just, 3 or 4 degrees of slope. But whatever it is, and the average is the final speed divided by 2. All right. Now we're going to use that in the next few slides to talk about the distance traveled while accelerating. Now we've already talked about this a little bit, and we're going to talk about it some more from this angle. All right. Now the thing about an average speed is, if you have the average speed and you know the amount of time you go, just speed times time. Average speed times time times elapsed time, and that'll give you your distance. All right. So let's think about that. All right. So here's delta V. All right. And that's equal to A delta T. All right. And we know that delta V is equal to V2 minus V1. All right. And delta T, we're going to say that time T1 is equal to 0. And that'll simplify our delta T a little bit as well. So we're going to say, all right, we're going to start our stopwatch as soon as she starts. Okay, not 3 seconds before she starts, but right at the time she starts. So what that allows us to do is simplify from delta T to just write down T. And what that really means is that this T is the total travel time from the moment Joyce kicks off down there until the minute she hits top speed down here and then gets off and starts to stop herself, which you saw her do. Okay. So V2 minus V1 and then AT. So that's all good. And so it's we're trimming down the notation a little bit, but it traces back to delta V equals A delta T. Now delta V equals A delta T. That formula tells you, and you might want to write this down again, the amount of speed, delta Q, that you acquire under acceleration for a certain elapsed time, delta T. Okay? If you're accelerating, you're either gaining or losing speed. All right? If you're just going in one direction. Okay, now if you change direction, it's a little different. But if you're going in one direction, in other words, straight down the ramp, you're either slowing down or speeding up. And the amount of new speed that you acquire, delta V, is just how long you're accelerating times the amount of acceleration you have. So A delta T. All right? So let me turn this off. Oh, I forgot to pick up my prescription. I'm going to have to do that when I get home. Dude. Man, I forgot that. Right, so now also V1 is 0. It's at rest. Up at the top of the ramp where Joyce was standing before. So this formula simplifies down. So on the left, we don't even have to write in V1. We just write in V2. Right, so there it is. V2 equals AT. Nice. All right. And so there's the time, her final speed down at the bottom. If you know the acceleration and the total travel time, you can calculate her speed down there. Okay. Now, let's put that into the average speed formula. Okay. So here we go. V bar, V average. V2 over 2, yeah, okay, good. And we now know that V2, if we make a few simplifications, is just AT. So V bar is AT over 2. All right, just a little straight plug-in. All right, now let me pause for questions. We're doing a little bit of algebra here, and I'm trying to go step by step so that everybody can, kind of follow along and not get too psyched out. So let me pause for questions. Rowing team, do you guys have questions back there? I see you consulting with each other, or I could hear you talking to each other. Okay, good, 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 good. Yeah, I'm trying to use words for each equation, and so that you can, because a lot of people they get really nervous in a class like this. They get really nervous about having equations and stuff, and I understand that, and I try to. And I've got methods. We're going to go over one of my top secret methods of helping you be less nervous about equations on midterms and stuff. But let's finish this discussion. All right, now this is an average. It's basically it's based on the idea of add them up and divide by 2. Which we did a few minutes ago. So this generic idea of average speed. Average speed times elapsed time is total distance. Speed times time. All right. Now we got another formula here for average speed. All right. And this one involves acceleration. It's acceleration times how long you're accelerating, t, and it's divided by 2. All right. So if it takes her 2.6 seconds to go down the ramp, we should have timed you. So if it I don't think it was 2. I think it was a little bit more than that. But let's say it was 2.6. That means that at 1.3 seconds you were at the average speed. That was your instantaneous speed. Okay. But we're still talking about average speeds here. Now, what's the formula for change in position from average speed? Delta x equals v bar times delta t. Now, delta t, we already made that simplification. That's t. We'll do it again here. Right? So the distance, so instead of delta x, we'll just call it distance. Okay, v bar, that's at over 2. And then delta t, let's use that simplification again. We'll just call it t. If we start the stopwatch up at the top of the path, then we can call delta t just t2 or just t. All right? So there's our equation. Now, if you look at that, there's 2 factors of t. So it's actually there's a factor of a in the numerator and a t squared, and down in the denominator there's a factor of 2. So another way to write that is this, 1/2 at squared. And that, my wonderful students, is the formula that we talked about last time, the distance traveled for a velocity triangle. All right, so let's put this together now. Distance under acceleration formula is 1/2 at squared. And you can think of it in terms of the velocity graph as, you know, constantly accelerating down the slope. She's getting faster and faster as she goes down. So that would be a triangle on a velocity graph of some kind. And, you know, we did that, like this one here. That was for a free fall velocity triangle. And, you know, Joyce's velocity triangle, we might just make it positive, so it would be like a, you know, triangle going up to the, from left to right. But anyways, it's a triangle on the velocity graph, and it comes from using the definition of acceleration and the distance at average speed formula. In other words, delta x equals v delta t. All right? And that's down here next to the 2 grizzly bears, or the 3 grizzly bears, 1 big one and 2 little ones. All right, so that's kind of nifty. All right. So if you think about distance triangles, that's the same as using the average speed concepts, add them up, divide by 2, and the, you know, distance equals speed times time, and knowing that it's a constant acceleration. So there's 2 different ways to look at it. Now, now that we've done this distance triangle business, let's kind of do a little recap. So let's report to the dean of our college, Professor Galileo. Let's report on what we know. Constant velocity, delta v equals delta x equals v delta t, or for simplicity, d equals vt. Distance equals speed times time. You know, that's a good way to write it. And for this one, the velocity graph is a horizontal line segment, and you form a distance rectangle. Now, that's the first polygon that we worked with on Tuesday afternoon. All right, the tortoise's velocity graph, and you know the +1 meter per second velocity graph, where it was just a straight line across for 2.5 seconds. Okay, that's a distance rectangle. Now, and that's for constant velocity. Now, Professor Galileo, we must also report accelerating systems, which greatly interested Galileo, of course. And if you make this simplifying assumption that it starts either from rest, so VI equals 0, or if it comes to a stop in which VF equals 0, then the change in position is 1/2 at squared. And we can use this formula here. All right? Distance equals 1/2 at squared. And on a velocity graph, that's a sloped line segment. And then the triangle is formed between that line segment and the time axis. So that's the distance triangle. Okay, so those 2 formulas, one corresponds to a distance rectangle on a velocity graph, and the other one corresponds to a distance triangle on a velocity graph. And remember last time, Tuesday, we were talking about the distance triangle, 1/2 base times height? Yeah, that 1/2 in the formula, 1/2 base times height, it's the same as the one we have here. It's also the same as the one, add them up and divide by 2. All right? It works both ways. It's pretty slick. Okay? Now, let me ask you this. What if the velocity doesn't change uniformly? In other words, what if you go from an acceleration at one level, like if you're on a ramp like this and then at halfway down the ramp it gets a little bit steeper, so the acceleration is a little bit better. All right, so if you raise your hand if you've ever been snow skiing. That's a fair number. Now for the rest of you, snow is this white crystalline substance from water that when it's really cold out and you get a lot of it and you can slide on it and stuff and make snowballs and whatnot. So you guys in Florida have never seen it. I haven't seen it in 15 years except on the internet. I used to live up in Vermont, and before that I lived in Montana. And there's always, in Montana, where I lived, up near Yellowstone National Park, just up the road from there, the mountains there, I've seen snow in the mountains every month of the year except July. And a lot of the old timers will tell you that they've seen it in July too. It's a little more rare. And I know that, actually, I take that back. I have seen it in July. I remember one time I went hiking for 4th of July. We just went out for something to do. Some friends of mine and I up this 10,000 foot mountain, and we got and on the way up, it was 4th of July, so there were a lot of people out for a hike. And I'll never forget, there were these guys in shorts and t-shirts and hiking boots, and they on their back they had their skis and they had their snow boots, in their knapsack and stuff. And there was in 4th of July, where I lived up, high enough, there were still that summer there were still patches of snow big enough you could ski on them. It's incredible. And up further north in Glacier National Park, you can ski all year round because those are glaciers. There's always snow up there year round. But it's incredible out there. If you ever go out west, one of these days I'm going to head out. Much as I love UCF, I'll be returning to Montana, hopefully, if things go well. Anyways, what if velocity doesn't change uniformly? Like you're skiing and you're going down a nice, easy slope, what they call the bunny hill, nice and slow for snow bunnies, just the beginners or for practicing and stuff. And then all of a sudden it gets really steep, down the pipeline. What happens then? Well, you can handle that, So let's get to that. Now, before we do that, I want to take a little mental break here and give you a little bit of modus operandi for exam 1. How are we going to handle formulas on exam 1? I mean, it's coming up in a few weeks. You'll have to make some calculations. You'll have to think with some of the formulas, even if you don't make a calculation. I might ask you, well, what part of the formula does this signify? Stuff like that. So even if you don't have a calculation, you still need to think about it, and that's actually the hard part. So how do I handle formulas? Well, a lot of people ask me, Dr. B, are we going to have a formula sheet on the exam? And the engineering department, they live and die by formula sheets. Those guys over there, they're always asking me. But I never, ever give a formula sheet. But what I do give is formula matching. So the first few questions, you're going to have a formula over here and like a concept over here, or you're going to have 4 formulas and 5 concepts, and you match the concept to the formula. And we're going to do it today in iClicker. So turn on your iClicker. We got another few multiple choice questions coming up here. And here's what it looks like. Okay. On the test, it'll be, like I said, a couple concepts, 1, 2, and 3, and then formulas A, B, C, and D. Okay. Or it might be formula 1, 2, and 3, and concepts A, B, C, D, and E. All right. So the formulas will be there for you, just like in the engineering department. Okay. But you actually earn a point for identifying it. Right. So you don't have to memorize. All you have to do is recognize. All right. So you can't like totally be ignorant. But I don't want you to go around memorizing formulas because that's, because you're going to have this, it's going to be just like this. Okay, so there's 4 formulas over there. And let's do the first question together. Matching formula number 1. Which of these is definition of acceleration? Go ahead and vote. Jet, I saw you whispering the answer. Okay, 5 seconds to vote, starting right now. 4, 3, 2, 1, 0. Okay, let's see what you guys voted for. Yeah, a lot of you voted for D for some reason, which is actually good because that is the correct answer. Okay, so that's the one you would bubble in. Okay, for number. So then you go to number 1 on the Scantron sheet and you bubble in D. All right. Now let's try the second one. Free fall position as a function of time. Whoa, you guys are fast. You're blazing. And so on an exam, I'll have the first 3 or 4 questions. A few formulas, maybe 4 or 5 questions. And sometimes I put the formula right in the question. If I run out of space, I might put it right in the question. Like the question might be, as you know, the acceleration is delta v over delta t. Therefore, what is, and then I'll ask you a question. So sometimes I do that, but most of the time it's up in the matching. Okay, 10 seconds to finish voting. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys voted for. Uh-oh. We got some splaining to do. Look at that. We got a spread of answers. The previous answer, everybody got it. But this one, no. The answer C is correct. And for those of you that voted for B, B is actually something we haven't studied yet. We haven't studied anything yet about forces. And A is something from quantum field theory. So we're going to get to that in like the last week or 2 of the semester. But you'll be able, by the time the first midterm rolls around, you'll be able to tackle these. Okay, so just write down, etc. Okay, now any questions about this? Fire ahead. What is D? G? Oh, G is the acceleration of gravity. 9.8 meters per second squared. Yeah. So it's a drop triangle. That's a, what is your name again? Brianna? What? Melissa, close. Okay. Melissa, it's a 1/2 something t squared, right? Distance triangle, accelerating. In fact, it's free fall acceleration. Okay, that's something that we'll continue talking about. Now, before we did this little interlude about matching formulas and stuff, we were talking about, well, what happens if the acceleration changes? And the thing, another common example, in addition to like skiing and going from relatively shallow slope to a very steep slope, another example is one of these big rockets over here at Kennedy Space Center. Right? Those things lift off. And the interesting thing is they'll, if they put the rocket motor at full blast, it'll develop so many horsepower of power to push that thing up in the air. All right. But what you don't know, or you may not realize, is to put it at max throttle, max horsepower, you're losing a lot of jet fuel or a lot of rocket fuel out the nozzle. So the entire rocket body, everything in the rocket gets lighter and lighter. And therefore it's easier to accelerate. So up there at Kennedy Space Center, they're going upward and they keep accelerating. So they start at a fairly low acceleration. But for a manned space flight, one of my professors in grad school was an astronaut, shuttle astronaut, Lauren Acton. And I asked him one time, what's the biggest acceleration you guys get on launch? And he said about 3.3 Gs, 3.3 Gs of acceleration. So 3.3 times the acceleration due to gravity here. So 3.3 times 9.8. Upward acceleration, all right? Now, the other thing that's happening, besides them losing a lot of mass and therefore being easier to accelerate at full blast, the other thing that's happening is the air is getting thinner, so there's less air resistance. And so that makes it easy. So it's pretty complex. And they got half the PhDs on the planet working on exactly where that rocket is going to go, millisecond by millisecond. Okay, they don't do it every 1 second. They do it, fantastically small increments of time, but they could do it. All right, and that's what I want to talk about now. How do you handle something where the acceleration is changing? All right, so now there's a great movie that you may have seen. Raise your hand if you've seen this, Hidden Figures. Oh my goodness, it's one of my favoriteest movies. And these are the movie stars in the movie Hidden Figures. But here are some of the real ladies in Hidden Figures. This one's Dorothy Vaughan, right here. And she was the queen of Fortran down there. Just when they move. And so for those of you that haven't seen it, it was this drama of these black women that were segregated, just like Virginia did in those days. Florida too, in the 40s and 50s, but they still were able to work at NASA. And this group in the movie, they were called calculators. They did all the calculations by hand and with adding machines and stuff like that before computers. And Dorothy Vaughan in the 50s, after World War II, they were just starting to develop computers for research. They started using them in World War II for code breaking, for breaking the Enigma machine, which was the German cipher code machine. And they broke it. They used computers to do it and math, buku math to do it. And then after the war in the 50s and then into the 60s, they would use computers that would, three of them would easily fill this room. And less powerful than your iPhone computationally. So it's amazing what they did. And so Dorothy Vaughan, and so that's the drama, the black women calculators, they were segregated from the white women calculators. So they were looked down on at all the horrible things of segregation. But they prevailed and they broke through. And because they were just, they were good calculators. And Dorothy Vaughan was the chief. And she was able to learn how to program in Fortran. And she taught all of her crew how to program in Fortran. So by the time the computers came in, her group was the only ones that knew how to do it. And so they ran, all those rockets going to the moon. Yeah, Dorothy Vaughan and all her, and plus a bunch more people. It's a big program. It's a lovely movie. And so let's do some more clicking about Hidden Figures and how they handled the trajectory of John Glenn's spacecraft. All right. So let's do. I want you to hit the refresh key. Okay. Okay. Hit your refresh key, and you should get a letter. Okay. You're going to do a short answer. Now I want you to type in a word or phrase Okay, so this is not in code or anything like Tuesday. A word or short phrase that describes the motion of an object whose vertical velocity, Vy, graph is shown. Think carefully. All right, so a word or phrase. And I'll grade everybody correct on this. It's kind of a survey. You know, I'm just curious to see what you type in. And just do that. Hear that? All that clicking? I love that sound. That's the sound of students thinking and making decisions. And you know, the thing about this is, you know, with this, you can type in, everybody in here can type in a different answer and it can still be right. And I love that. Including the guy that typed in, was it this class? P, 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 P. That was the best. You know, I gave that question to my students in my engineering physics class, Physics 2048, and nobody came up with that. So you guys are the geniuses on that question. And don't, you know, and I'm not saying that lightly. I mean, you guys are just as smart as those engineering majors, if not smarter. Tell me about it, right? I mean, you know, engineering majors always think they're pretty sharp, but you know, you guys are sharp. You guys have just as much brains as they do. And that's what we're trying to do here, is to get you to think and use that blob of gray stuff at the top of your neck called your brain. All right. Let me take a look at some of your answers here. Nice. Nice. Uh-oh, I see some misspelling, but that's all right. Good, good, good. All right, 1 minute. And when you have your word or short phrase, hit the send key. I see there's a smart guy here. Somebody's trying to mess with my mind. It's kind of hard to get all these answers. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Let's take a look. Some of these are good. Fast. Yeah, faster and faster. Accelerating. A lot of those. Let me go down the screen here. It's really hard to move this cursor. Here's a word up there, exponential. That may or may not be exponential, but whoever typed that in is thinking about a certain kind of acceleration. Fall fast, faster, faster, higher. Yeah, so, and that's right. The higher the graph is, the faster it's going. So you can see that the speed is changing. But the one thing that you have to remember is on this one, it's curved. There's a curve to it. So make a note of that. Try to draw a sketch of this. And here's what the hidden figures was about. How do you figure out the area for this? You know, the area under the velocity curve is the distance that your rocket has moved. But if your rocket is getting faster and faster like this, you know, and it's not accelerating at a constant acceleration, it's getting steeper and steeper. How do you get the curve? All right, so let me pause. You go to your graph And you take a little slice of it like this. So draw in a couple little lines, like what I have, let's see, over here, right over here. Okay, those two lines. And I did those two, and mine are 90 and 104 pixels high. Okay, I measured it real carefully. All right. And they're also 50 pixels across. All right, so they form a trapezoid. If you connect the dots, and the width of it is delta t, 50 units across. So that might be 50 milliseconds or 50, 50 hundredths of a second. If it's a stopwatch. And then you do that little trapezoid. And you know what all a trapezoid is? Go ahead and write this down. Trapezoid is a right triangle on top of a rectangle. Dun, 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 dun. That's it. It's pretty easy. This kind of trapezoid anyways. So all you have to do is a lot of little delta t's and then calculate the trapezoid. And then you're looking good. So here's the thing that we're going to do. And we're going to do a lot of little delta t's if we're going to try to tackle that hidden figures curve. Now next time we're going to talk about Newton's laws of motion. And so we're going to dismiss a little early. And I want you to do homework too and see if you can watch Hidden Figures on Netflix or something. Okay, and homework 2 will be ready tonight, maybe in the morning, and it'll be due next Tuesday. And